Now Thomas Steinke is going to tell us the second part of adaptive data analysis.
Thanks. I don't think I can deliver on all the promises that John made about my talk. So I'm going to be talking about the same topic basically, and I'm going to be talking about a bunch of different works, but most of what I'm talking about is actually based on joint work with Vitaly Feldman, who is here in the audience. So as you probably noticed, John and I submitted IID abstracts. But the good news is that we did actually coordinate our talks, and I am going to talk about something different. So I'm going to talk to you, first of all, just give a very brief recap of the setting that John talked about, but I'm going to talk to you about distribution-dependent accuracy guarantees. I'm going to talk about really focusing on the sort of accuracy guarantees that we can get in this adaptive setting. And then at the end, I'm going to talk about using weaker notions in differential privacy and connecting these ideas to information theory, and still retaining the generalization properties. Okay, so John did a great job of covering the motivation. Basically, adaptivity is a complex issue that seems to be lurking in the background, causing a lot of problems. And statistics and machine learning and all kinds of empirical sciences. So John gave us a model in which we can study this formally, so I'll just recap that model. So the two main actors are you have a population that you're trying to study, which is a distribution, and you have someone who's interested in that. And they're basically asking some real valued queries. They have some function, they want to know what the expectation of that function is on the distribution. And the way they compute that, because they don't actually know what the whole population is they sample n IID samples from that population. They stick that into their favorite algorithm, and then they start asking a bunch of queries. And a good example of this would be, the analyst is just asking, give me a gradient, because they're doing gradient descent. And the thing that makes this adaptive is that the queries are being specified one by one, and each query can depend on the previous answers, but in the non-adaptive setting, that's easier. You specify the queries all at once. Okay, so I've specified what the model is. Now the question is, how do you measure accuracy? And the definition of accuracy that John spent most of his time talking about is sort of an absolute accuracy guarantee. So the answer that is reported by the mechanism relative to the true answer, which is the expectation on the population, should be close, just as real numbers. So the question is, could we hope for better than that? And we could actually hope to get a better answer if we take into account the distribution. So what I'm going to talk about is distribution-dependent accuracy guarantees. So we could hope that these answers are close in a way that depends on the standard deviation of the value. So this is the accuracy guarantee that you would get if you had t fresh samples from the distribution. And you can prove this just by taking a Chernoff, a Bernstein inequality or a Chebyshev inequality to get this sort of concentration bound. So this is the main difference between what John was talking about and what I'm going to be talking about now. Okay, so any questions before I move on to actually talking about the results? Okay, so this is just a recap of the result that John gave. So we have an efficient algorithm that gives us a bunch of answers to adaptive queries with some accuracy guarantee that's sort of a fourth root of k. One important difference between John and me is that I use square root rather than fourth root. It's a difference of taste. And what I'm going to be talking to you about now is a guarantee which looks very similar, except now I'm going to bring in the variance of that query. So I hope you can sort of see that this result dominates the previous one, except for some annoying log factors. And basically that's because the variance is at most 1. So the goal is to get accuracy guarantees that scale with the variance, but we still get some absolute error beta, but ignore that term. So why might this be interesting? Well, I want to argue to you that you actually, in practice, you often do want to ask very low variance queries. And one example is if you're testing the accuracy of your classifier. Sure, if your classifier is 50% accurate, then there's no difference between these results. But you've got bigger problems than that. If you've got a classifier that's 99% accurate, then the variance is going to be much lower. So you're going to get much better estimate of the accuracy using these results. Okay, so the previous work that John was talking about, the accuracy guarantee scales with the worst case sensitivity of the query. So if you take the largest possible value and the smallest possible value you could possibly attain, and it doesn't really matter what probability though is attached to those. Whereas what I'm talking about, the accuracy guarantees with the standard deviation. And the sensitivity is essentially irrelevant. I would argue this is the natural scale of things. If you're doing normal statistics, we aren't worried about adaptivity, the standard deviation is basically the scale that you use to measure your accuracy. And as I mentioned, if you're trying to measure a binary query, such as, is my classifier making an error, you're going to get a pretty significant difference. If the true error is p, then the accuracy guarantee that scales with variance is going to scale with root p. And I should also add that the extensions that John talked about, where you exploit having a low dimensional U, those also carry over here. And essentially the message that I want to push to you with these results is that if you're answering k queries that are adaptively chosen, what we can do is we can the obvious thing you do is collect t fresh samples for each query. That of course would give you k times t samples in total that you need. What we're saying is you can get away with square root k times t samples. So you're able to sort of simulate having a lot more data than you really have. Okay, so how might I go about proving such a result? So I'll just tell you what the ingredients are. So the first ingredient is the connection between stability, or differential privacy, and generalization. And that's exactly what John was talking about. And we know that differential privacy gives us these nice generalization guarantees, and the important thing is that it is able to compose adaptively. So when you run multiple differentially private algorithms, even if you're running them in an adaptive fashion, it's still differentially private. So the other ingredient is that we add in the median of means tricks. This gets used in various places, but basically the idea is that if you take the median of a bunch of values, that's going to be much more well-behaved than, say, an average in some sense. And of course, we need to have a differentially private algorithm to compute this. So what does the algorithm look like schematically? So we get a bunch of queries, and for each query we're going to do the following. So you take our whole data set, and you split it up into a bunch of sub-data sets of size t. And you evaluate the query on each of those sub-data sets, and then you compute an approximate median, and that's your answer. So comparing that to the algorithm that John was describing, in the previous algorithm you compute the query on the whole data set, and you just add some noise. So our algorithm is a bit more complicated, but as a result we get these improved accuracy guarantees. So what I mean by computing an approximate median, that's something that I have told you is an essential ingredient. What do I mean by that? Well, I said you compute a bunch of values, and those values are going to give you a distribution, but it's a discrete distribution. So the CDF of that distribution is going to look like this blue line. And that's approximating some true distribution, which is if you had infinite data. What we're looking at is, if I look at something that's between the 60th percentile and the 40th percentile, any pre-image of that is going to be what I call an approximate median. And the reason differential privacy comes in here is that we use it to say that the red line and blue line, which is the true CDF and the empirical CDF on your data, are close. And the other ingredient, as I said, is having good differentially private algorithms. So I'll give you so we have algorithms that will find some pre-image of these percentiles. Yes?
Can you just remind me, the assumption that you have on the queries is only about the second moment? That's all you have?
It's even better than that. We just assume something about its first moment, and even that is, we can go even weaker than that. All we're assuming about your query is that, yes, so what we're assuming about the query is that basically you're interested in an interval, and your query falls into that interval with probability at least, I think 51%? How low can we go? I think 75 is.
I think we use 75, but I think anything better than.
Yeah, but basically all we're saying is that your query falls into some interval with probability at least, say, 51%. Now, if you think about it, if I get a whole bunch of samples and I take the median, then with high probability, the median is going to fall in that interval.
But I thought the size of the interval was depending on the variance of the query. I'm sorry.
Right. So what I'm saying is that you could even relax the variance. You could use.
Oh, I see what you mean. Okay.
You could use like a first moment, or you could use just whatever is like the interquartile range.
Sure. Okay, I see. Okay.
So we can get away with extremely weak assumptions. Okay, great. So I've given you a schematic of how the algorithm works and sort of the two ingredients, how they fit in together. So I just want to explain to you how you would actually compute an approximate median in a differentially private manner. And it's actually extremely simple. I can just explicitly write out the distribution. So I'm going to output a value A with probability proportional to sort of how far its CDF differs from the desired value. So if the CDF is at a half, this is going to be its maximum value. And if we actually plot this out, you can sort of think of it as here are your data points on the real line. And I have my probability mass function sort of peaking at the true median and sort of decaying exponentially as I go further away. I'm just sampling from that distribution. So computing a differentially private approximate median is actually quite simple. But I will add that you can come up with algorithms that are a lot more sophisticated than this, a lot more complicated, and they get you 2 to the log star dependence on the total range. But I won't talk about those. Okay, so any questions about the algorithm? So the key win of doing this whole splitting things up and taking a median is that changing one of these inputs can only you're only changing one of these guys. It can't really change the CDF very much, and therefore it can't move the approximate median. But if I were to take a mean, then I could change things a lot more. So I also mentioned that there are various extensions. So we can extend this to any real valued estimator. I don't need to be just asking for the expectation of some sort of single function of a single data point. I could try estimating the variance of the distribution by taking 2 data points. Any estimator, really the only assumption that we're making here is that it's real valued. So things get a little problematic if you look at things that have more complex values. But that's pretty high generality. Another important extension, which John briefly mentioned, is the reusable holdout. So the idea behind that is that it's very expensive to answer k adaptive queries if you know nothing about them. But you can actually get away with a lot better if you are trying to just use it as a holdout set, which is to say that you have a guess for each answer, and you're just trying to verify whether that guess is correct. And you can also get better results, so you get a logarithmic dependence on the number of queries, if you assume that the data domain is reasonably small. But again, as you asked after John's talk, we're starting to get this t to the 3/2. So and when you rearrange that, you're getting this cube root rather than square root dependence, which it's unfortunate, but we don't really know how to avoid that. Okay, cool. So the message that I hope I've managed to communicate to you, which I will repeat, is that we're able to sort of simulate having k batches of t fresh samples using sublinear and k samples. Okay, great. So this is the algorithm that I told you about. It's wonderful and beautiful, but it's kind of complicated. You know, are you really going to be doing this in practice? So, you know, the question that I want to address in the remaining time, how much time do I have, by the way? 10 minutes. Okay, great. So the question I want to address with the remaining time is there a simpler algorithm that we could use? And I will answer that question in the affirmative. So the previous algorithm that's just giving you guarantees that are absolute, doesn't depend on the distribution, is just to compute the empirical answer and add some Gaussian noise. That's the previous algorithm, very nice and simple. And the question is, you know, could we modify this algorithm, keep the same schematic, and still get guarantees that scale with the variance of the distribution? And the answer is yes. So what I want to talk to you about is an algorithm that takes the empirical answer and adds Gaussian noise, but now the Gaussian noise is going to scale with the variance of the query. So this is the empirical variance, but that doesn't really matter. All right, so previously you just have sort of a 1 over t and no scaling with the variance. Now we can actually show that this particular algorithm attains this accuracy guarantee. So you're probably thinking, what is this? It's got some expectation of a maximum of some ratio. So let me try unpacking that for you. So this is the error that we're getting for the jth query, and this is the sort of desired bound. This is you know, the variance scaled by 1 over t plus some sort of base factor. And we're saying that the expectation of this is small, which in particular means that with decent probability it's small. So I could take, for example, a Markov inequality bound and sort of show that with reasonable probability the error, the maximum error, scales with the variance. So maybe as a comparison point, this is the result that we had for the complicated mechanism with the approximate median. And if you were to just take Markov's inequality, you'd get a similar result, but the beta would be not as good. So the dependence on these beta parameters is worse, but otherwise it's basically the same result. Okay, so I've told you this algorithm that sort of seems kind of natural. You take your empirical answer, you add some noise, but you make that noise scale to the accuracy guarantee that you want. But how do we actually analyze this? So previously we've used differential privacy to do the analysis, but it turns out this algorithm just doesn't satisfy differential privacy at the level that we need to prove the desired goal. So what we're actually going to use is a relaxation of differential privacy, something that's weaker than differential privacy. And we call this average leave one out KL stability. So what does that mean? So if you look at the distribution of the algorithm on some input data set S, and then we're going to compare it with KL divergence to the same algorithm, but where you remove one of the data points. So remove a data point at random, so we're averaging over the n data points. And we're going to say this is smaller than epsilon. So this is a relaxation of differential privacy in two different ways. So the first is that KL divergence is weaker than the similarity guarantee that you get in differential privacy. Now, formally that's not quite true, but morally that is. And this weakness is why we only get a bound that has the expectation. We don't really get these strong high probability bounds that we were getting before. The other relaxation is that we're now averaging over the n points in the data set. Previously we said pick the worst data point and replace that. And so what we're now allowing is that some, if you think of this in terms of privacy, some of the people might actually have their privacy seriously harmed, but on average, people's privacy is not very harmed. So, in comparison, maybe I just pick a random person in the room and completely violate their privacy. This would, on average, be okay, but would certainly not satisfy differential privacy. So, first things first, adding the scale Gaussian noise that I told you about does satisfy this definition. That's a kind of messy calculation, but it's true. And sort of the really magical property that got me excited about this is that this definition composes adaptively. What do I mean by that? I mean that if you answer k queries, each adaptively chosen, then the epsilons just add up. And that's really the whole reason why we use differential privacy here. So I think a lot of people wonder why differential privacy is being used in this regime where privacy is not a concern. And the reason is this ability to compose adaptively. And this definition is able to satisfy that. And of course, the final property of the three that we want is that this guarantees some generalization properties. Okay, so here's the definition, and now I want to tell you how you get some generalization properties from this. And the key lemma here is that if you have this average stability, and you take a random IID data set, then the mutual information between the data set and the output of the algorithm is bounded by epsilon n. And this bound on mutual information has been identified as a really good way of proving generalization results. In particular, Rousseau and Zhou showed basically that once you have this bound on mutual information, you're able to get bounds. So bounds on generalization. So you might be wondering what this complex inequality here is. This is actually one of my favorite inequalities. And basically what it's saying is that, okay, if the mutual information is small, and then I can relate the expectation of some arbitrary function of the data set and the output to the moment generating function of that if I have an independent data set. So if we pop up the theorem that we're trying to prove, let's look at this quantity here. This is my f of s and q. This quantity, if the queries were independent of the data, and I just use the empirical answers, this would be very well behaved. And so that's telling me that this term over here is bounded. Stability is telling me that the mutual information is bounded, and that's giving me a bound that is precisely this thing here. Right, so if the mutual information between these two things is 0, that means they're independent. That means the queries that have been asked of your data are independent of the data set, or just in the classical non-adaptive world. And this is just a quantitative version of that statement. If you have bounds on the mutual information, you're also going to get some relationship to the non-adaptive world. Yes?
So actually, I'm not sure I believe this theorem. So don't you need more assumptions now because you use the empirical covariance and you wanted to somehow concentrate around the true variance? In your algorithm.
Oh, yes. So we also need to show that the empirical variance is close to the true variance. So that's a separate lemma that goes into the proof of this main theorem.
But I don't see any assumption in the theorem that would say that this is true.
I mean, the assumption that I'm making is that these are bounded between 0 and 1.
Yeah, now you assume bounded.
Yeah. I snuck that in. Previously I just said there were kind of arbitrary real valued things, but I'm sneaking that boundedness assumption back in.
And then there's only into the second order term, this plus 1 over t.
Yes.
1 is from the range, so you kind of just move it to the second order.
Very good. Okay, cool. Thanks.
Okay, so the key points is that adding scaled noise is going to still give us adaptive generalization guarantees. So that's kind of really nice. I think it's nice that we have a simple algorithm that's still giving us guarantees that scale with the data distribution. And I also really like the fact that we have this relaxed notion of differential privacy, this average stability, and we're able to show this is a useful way of ensuring generalization. And again, the key property that sort of makes this thing interesting is that it composes adaptively. And the analysis through mutual information, I think, is a very clean observation due to Rousseau and Zoe that this is a very sort of general way of understanding overfitting and generalization. Any questions at this stage? Before I wrap up? Yes. Okay. Great.
People have used the error correcting codes and things like that for dealing with different estimators. You have like multiple estimators, you take the average mode, or you actually look at the deeper, the features and make more advanced codes. Is there a relationship? Because they also talk in a similar language of relative entropy and stuff like that.
That's a good question. I don't know of a connection. Let's put it that way.
They do use things like that in bagging, like you have different estimators, you want to combine the results somehow, and sometimes you just eliminate some of the features or add some in the way it looks like error correcting code.
That's an interesting question. I don't know.
Thanks again.